All right, so number 31 on page 501 is an Olympic diver with a mass of 54 kilograms. So mass of the diver, let me make that. Mass of the diver is 54 kilograms. Standing all the way out on the end of a diving board that's 3.8 meters long and that's uniform. So because it's uniform, that means the FG of the diving board is exactly halfway along its length. So this distance will be 1.9 meters. Okay, and the mass of the diving board is 25 kilograms. But now notice this time it says the fulcrum supporting the diving board is 1.3 meters from the bolted end. So here's the bolt, here's the fulcrum. So it's not in the middle this time. And this is F of the fulcrum. And so this distance is 1.3 meters. And the bolt should be putting a force down, F of the bolt. Okay, and it wants to know how big is this force that the bolt's putting down. Why is the bolt putting a force down? Because if I hold it at the fulcrum, these two on this side, the diver and the diving board, are going to make the diving board want to rotate clockwise. If the bolt was acting up, then the diving board would rotate clockwise because everything would be, all the forces would be making torques wanting to make it rotate that way. So the bolt must be going down to counterbalance it out. Okay, so we go over here and we do sum of the torques should equal 0. So there's a torque from the bolt, there's a torque from the fulcrum, there's a torque from the diving board, and there's a torque from the diver. Now, I'm going to assume we'll pick our pivot point at the fulcrum because that's really where it is pivoting. So if we do that, fulcrum torque will go to 0. Again, hold your writing utensil at the fulcrum. The bolt will make it rotate counterclockwise. The board and the diver clockwise. Counterclockwise is positive. Clockwise is negative. Okay, now we can sub in R of the bolt, F of the bolt, sine theta of the bolt, minus R of the diving board, FG of the diving board, sine theta of the diving board, minus R of the diver, FG of the diver, sine theta of the diver. All right, if we take a look at the thetas, again, they're all 90, which means the sine thetas will all be 1. So we'll have R bolt, F bolt, minus R of the diving board, M of the diving board, G, minus R of the diver, M of the diver, G equals 0. Now note, the forces from the diver and the diving board are both the weights of those two things. But the bolt is not the weight of the bolt. The force that the bolt applies has nothing to do with its weight and everything to do with how tightly it's attached. So this is not an FG, even though these two are. G's cannot get canceled because there's no G in the first term. We're solving for F of the bolt. So take the other two terms over. Diving board, G, diver, G, and divide by R of the bolt. So, diving board, it's a uniform board, so it's 1.9 meters from the end, but we want to know how far is it from the fulcrum, because remember the R is from the pivot point to the force. So if it's 1.9 meters from the end, and the fulcrum is 1.3 meters from the end, then this R should be 0.6 of a meter. The mass of the diving board is 25 kilograms, 9.81 meters per second squared, plus how far is the diver from the fulcrum. So the diver is 3.8 meters from the end, the fulcrum is 1.3 meters from the end, so the diver should be 2.5 meters from the end. So 2.5 meters. The mass of the diver was 54 kilograms. times 9.81 meters per second squared. And how far is the bolt from the fulcrum? It's 1.3 meters. Okay, type all of this into your calculator, and when you do, you should get 1131.92 newtons. Number 31, done. Number 32 is going back to that arm that we saw in question 30 the other day. Okay, so number 32 has an arm that I'm going to just draw as a straight line, because that's what my artistic ability allows. And the elbow joint is here, and that's going to be our pivot point. And so it says you're holding a 16 kilogram steel ball. So this is going to be FG of the ball, and the mass of the ball is 16 kilograms, which is like 35 pounds. So this is a really heavy ball, even though according to the picture it's pretty tiny. While keeping your forearm level, that means the thetas are going to be 90 here. And your forearm has a mass of 2.3 kilograms with the center of mass as shown in the diagram. So that dot, that's not quite exactly halfway along the length, is the FG of your arm. And it's telling you the mass of your arm is 2.3 kilograms. And it should make sense that it's not halfway because our arm is in uniform. Given the dimensions in the diagram, what force would your bicep muscle have to exert on the bone of your forearm to hold your forearm in place? So your muscle is pulling up here. So we're looking for F of muscle. Oh, except maybe it's pulling up on the other side. It is. It's really over here. It's always good to look at the picture after you put your force in. So the F, according to the picture, is really on this side. Okay, and so it tells us that this little distance is 0.052 meters. It tells us the distance from the center of mass of your arm to the elbow is 0.15 meters. And then it tells us the full length of your arm. This distance is 0.34 meters. Okay? And it wants you to find Fm. So again, we're going to do sum of the torques. Has to be equal to 0. So there's going to be a torque from your muscle, a torque from the weight of your arm, and a torque from the ball. All right? Holding your writing utensil at the pivot point, your muscle's going to make it rotate counterclockwise, the weight of your arm and the weight of the ball clockwise. So positive, negative, negative. R of your muscle, F of your muscle, sine theta of your muscle, minus R of your arm, FG of your arm, sine theta of your arm, minus R of the ball, FG of the ball, sine theta of the ball. So again, if you're saying, how do I know which one's FG and which one isn't? If what's causing the force is the actual weight of the object, which it is in the case of the ball in your arm, that's the force. But it's not the weight of your muscle, it's the strength that you can generate in your muscle. Okay, but if you just held your arm out level, right, all day, if you held it straight, without anything in your hand, it would get tired just because your arm has a weight. All right, we're holding it level, so these go to 0. And so we're solving for muscles. So it'll be RAMAG plus RBMBG divided by R of your muscle. And this one's actually easier because they told you all the R's. So they told you the mass for your arm, or the R for your arm was 0.15, 2.3 kilograms, 9.81 meters per second squared. For the ball, it's 0.34 meters, and it's 16 kilograms, 9.81 meters per second squared, and the R for your muscle, 0.052. Type all of this in. The answer in the book, of course, is wrong, but you should get 1,091.36 newtons. Okay, we're almost out of time.